Recording in progress.
Good morning. Hope you're all having a good Wednesday. Kind of a small crowd here today, but I hope we'll get some more people. I want to encourage you in these live sessions to just speak out whenever you feel like you need to. Use your microphone or use your camera if you have to, or if you want to, because sometimes I ask questions and it's nice if I can get a spoken feedback, because I can be more spontaneous with it. Waiting for the chat sometimes takes a little while, and also people who are watching this later on may not get access to that chat at all, so they don't see at all what's happening in the chat. So sometimes if I ask a question, it'd be nice if you could just speak up and answer the question using your microphone. And that would really help a lot. It would help kind of keep the pace of the session going. Well, we're on to chapter 3 today. We just blew through chapter 2 in one day. Talked about the logic gates and circuits and the building blocks of computer systems. And today chapter 3 is kind of a continuation of chapter 2, because it takes the logic gates and the circuits and now expresses them as what appears to be algebraic expressions, because you have not plus and times and divide, but things like ands and ors and nots. We're switching symbols. We're not going to be using the words anymore. We're now going to be using the symbols for ands and ors and nots, but it's still basically the same thing. Any questions before we begin? No? We're all good? Okay. Well, here is the first slide I have for you, and this actually involves a little bit of problem solving. I've got two Boolean expressions, and I want you to show that these two, the one on the left and the one on the right, are equivalent to each other. And we're going to do so by basically making the truth tables for each one of these. And you remember what I said last time, that if you have two expressions, you have two circuits, and they appear to be different, but they have the same truth table, then they must be equivalent to each other. So to do this problem, the first thing you have to know is what these symbols mean. We've got three symbols on here. We've got this one that looks like a little inverted L. We've got this V, and we have this little thing called a hat. And actually, I'm going to swap those two around. Like that. So the top one means not. The middle one means and the bottom one means or. So what we want to show is the not of not A or B equivalent to A and not B. So I'm going to show you two ways to build the truth table for this. One of them builds out to the right, and the other one just builds down. the one that builds out to the right is probably the one that you're going to see most often in like another video, or maybe you look in another textbook and you see how these kinds of problems are solved. They build out to the right. They take up a fair amount of space, but it works. I need to bring up my notes here, so give me a moment. Here it is. So for this first one, we're going to start with a small table. We're just going to have a and b, our two variables. And we're going to write down all the possibilities. 0, 0, 0, 1, 1, 0, and 1, 1. So two variables, there's going to be 4 possibilities. And now we start building out our table to the right using some of the sub-expressions we see in the expressions that we're trying to prove. So out of all of these here, out of this not and, which of these do we do first? Well, we do the not a first. There's actually an order of operations with these Boolean expressions, just as there are with regular algebra. You can kind of think of the not as being kind of like negate. And is kind of like multiply, and or is kind of like add. And in fact, those operations are very similar to each other. Not only in terms of order of operations, but actually in what they do. That if I actually take the values of a and b and I multiply them together, actually do 0 times 1 or 1 times 1 or 0 times 0, I'll get the same results as if I did the and operation between them. So that's why and is a lot like multiply. And the same thing goes with add. If I actually do an or operation between them and I actually add them together using only one bit as the answer, then I'll get the same answer. So as far as the order of operations go, you do negation first, then you do multiplication, then you do addition. So we do nots first, ands next, and then ors last. Okay, so the first thing we're going to do here is the not a, and then in that column, I'm going to write 1s and 0s here. I'm just going to take the a column and invert it. Then the next operation is not a here or b, so I'll write that next, not a or b. And then to compute the values in this column, I just look at the not a column here and the b column here, and I perform the or operation between them. So I've got 0 or 1, which is a 1, 1 or 1, which is also a 1, then 0 or 0, which is 0, and then finally 1 or 0, and that's a 1. And then the last column here is going to be that whole expression, the not of the previous column. And that's easy to do. You just take this column and you invert it. So there's our truth table for this left-hand expression. Now we'll do the right-hand one. So again, I'll start with my a and b. 0, 0, 0, 1, 1, 0, 1, 1. And then the first thing I do is a not b. So I'll invert those values. And then finally I'll do an a and not b. So I'm performing the and operation between this first column and this third one. And I get 0, 0, 1, 0. And we can see that this and this column came out to be the same, so they've got the same truth table, so these two expressions are equivalent to each other. So you try that now for number 2. Go through the same procedure, see if you end up with the same thing. Now, the one on the right is easy to do, so I might as well just do that one for you. You work on the left-hand one. So work on the left-hand one. Tell me whether you arrive at the same column on that, in your answer column, as we did for the right-hand side. I'll get you started over here. Just A and B, 0, 0, 0, 1, 1, 0, 1, 1. And then the first operation to be done is the not A. So you'll invert the A column and write that down in the not A column. Okay, hopefully you're moving along on this problem. I'm working it out as well. So I've already worked out the not A and B column. And the last one is going to be the A or, and then the not A and B, which is just this column over here. So we're just doing A and this column. I'm sorry, A or, not A and, A or. And then we end up with the same thing. Okay, so there's two problems. We showed that they were equivalent by building truth tables for each one of them. I'm going to show you two more problems. The first one's going to involve 3 variables. Here it is. And so this truth table is going to have 8 rows in it. But I'm also going to show you how to do this a different style, where you just build one table and it's all really compact. And it works because we're using separate symbols for each one of these operations. So the first thing I'm going to do is I'm going to write down all the values for my variables. I've got x, y, and z. So I'm just going to write those down right below the variables. And we're going to go through all the combinations. So there's 8 of them. And now, looking at this expression, x or y and z, which of them do we do first? Do we do the x or y first, or the y and z first? So if you remember from the previous slide, And is kind of like multiply. OR is kind of like add. And the order of operations for those is multiply comes first. That means we're going to be doing the and first. So right underneath the and, because I got space right between them, I'm going to put the result of x and y. 0, 0, 0, 1, 0, 0, 0, 1. And then finally, I'm going to be doing the OR operation, and I'm going to do that between the x column and then that AND column that I just calculated. So right here in the space underneath the OR, I'm going to put the result of x OR and then that blue column that I've got on the screen. 0, 0, 0, 1, 1, 1, 1, 1.
Was the green your final answer?
Yes, for this table, yes. I'll highlight it. Or if you don't have a highlighter, you can like point at it or somehow indicate that this is the result column. Now for the right-hand side, again, I'm going to put down all the values of the variables, but I've got the 3 variables, but one of them's repeated. So I need to make sure that, first of all, I need to make sure that I don't put in 16 rows because I only have 3 variables. And the other thing to make sure is that for the repeated variables, which in this case is x, I need to make sure I put in the same values in the x column. So it's, and what you could do really is just look over here on the left-hand side and just copy whatever values you see there. So underneath x, I'm going to put this value of x. So I got a 0 here and a 0 here. For y, I'm going to put this value, and then for z, I'm going to put this value. Okay, so let me go through this. I'm going to go 0, 0, 0, 1, and then 0, 1, 0, 0, and 0, 1, 0, 1. So I need to make sure that my x columns here are identical to each other. And then I go 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, and then 1, 1, 1, 1. Okay, as far as order operations, I'm going to do this OR first. So that's fairly easy. I just do an OR between those 2 columns that are right next to each other. 0, 0, 1, 1, 1, 1, 1, 1. And then same thing on that right-hand side. An OR operation between those 2 columns. 0, 1, 0, 1, 1, 1, 1, 1. Remember, OR means if either of them is a 1 or both. So all you have to do really is just look to see if there's at least a 1 on either side. And then if there is, just put a 1 down. If they're both zeros, then put a 0 down. Okay, and then our answer column is going to be this and it's going to be the and between the 2 blue columns that I just did. So we have 0 and 0, which is 0, 0 and 1, which is 0, 1 and 0, still 0. Now 1 and 1, that's a 1, and then the rest are 1s and 1s all the way down. And then here's our answer column for that side. And we can see that both of these highlighted columns are the same. So they're equivalent to each other. All right, last one, same style. We have 2 variables, x and y, so our table is going to have 4 rows. And just make sure that we're writing the correct values down in each one of the columns. So I have only x and y here, 0, 0, 0, 0. Going to end with 4 rows, 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 1, 1. And then over on the right-hand side, I've got only one variable. I only have y, but my two tables need to have the same number of rows. So the table on the right, even though it only has one variable, I still have to put 4 rows in there to make sure that the two tables come out to be the same. So I'm basically going to copy this y column right here, or this one, 0, 1, 0, 1. And then the right-hand side is easy. It's just a not y. And that is the answer column for the right-hand side. Now on the left-hand side, we have nots, we have ands, we got ors. We got to do the nots first. So let's just quickly put those in. We got 1, 0, 1, 0 here, 1, 1, 0, 0 here, 1, 0, 1, 0 here. Now, between this and, this or, and this and, which one do we do first?
The and on the left side?
Yeah, we'll do the and on the left side. So I'm doing an and between this column, the x column, and the not y column. So let's see, an and, that's 0, 0, 1, 0. And then the next column will be the and over on the right-hand side. And I'm doing that between the not x column and the not y column. So I got 1, 0, 0, 0. And then finally, I do this or, and I'm doing that between these two green columns, the ones I just calculated. And we get 0 or 1, which is a 1, and then 0 or 0, which is 0, 1 or 0, that's a 1, and then 0 or 0, it's a 0. And this is my answer column. Oh, it's hard to see. Let me redo that in a darker color. I will pick, I don't really have a darker color that's different. I'll try this one. Maybe the key is to highlight it in something different. I'll try that. This one here. There we go. Yeah, that works. So it turns out, so we got 3 problems we just did. We did the ones on the first slide, and then we did the 2 on this slide. It turns out that most of these actually have a name. This first one here, number 1, that is called De Morgan's. De Morgan's basically says that if you apply a not operation to an expression, what happens is you negate each one of the variables. So the not A became just A, and the B became not B, and then the operation switches from and to or to and. So in regular algebra, it's kind of like sending a negate, through an expression. You negate each one of the values inside, but one additional thing is the operation switches. The one on the bottom is called absorption. And you can kind of see here how we had 2 A's in this expression, and one of them, this not A, got kind of absorbed, and went away. And then finally, number 3 is called distributive. That if I have x and y or z, no, let me say that again. I got x or y and z, it can turn into this. So sometimes we call distributive factoring. It's the same idea. The one on the bottom doesn't have a name. I just made that one up. So that's how you show the equivalence between two expressions if all you have are just truth tables. If you have kind of like no other tool at your disposal, you can always use truth tables. I know it's tedious work, but if you end up with the same values, the same columns in both the tables, then you know those expressions are equivalent to each other. But it can be helpful to work with these expressions algebraically. So, you know, in your math classes, you may have started with a complex expression involving several variables, and the instructions might be to try to simplify that expression, try to get rid of any unnecessary values or variables, or maybe to show that two expressions are equivalent to each other, and you may do some kind of transformation. You transform one into the other, or maybe you transform both of them simultaneously, and you see if you arrive at the same thing at the end. And so that's what I'm going to show you now. In order to be able to do this, we have to work with some properties of Boolean algebra. And a lot of these names you've probably seen before. Things like associative and commutative and distributive. You've probably seen those in the context of a regular algebra class. But these are the same things but applied to Boolean algebra. And some of them are kind of cool. You can't do them in regular algebra. And some of them are different. Now, it may help, actually, to switch the symbols here. Looking at all those V's and hats, it actually makes my eyes just go bonkers after a while. I like to actually switch the symbols over to a more algebraic notation, and then some of them make more sense because you've seen those patterns before. Remember I said earlier that and is kind of like multiply, and or is kind of like add, and negate is kind of like, a not is kind of like negate, except that instead of doing the little inverted L, I'm going to put a bar on top of the variable, and that means that a not operation has been applied to it. So here's what the same expressions look like, but in that new sort of mathy, algebraic style of notation. So this first one here, the associative, I'm just going to replace the or, the V, with a plus. And when there's a multiply, I'm either going to put a dot or I'm just going to join the two variables together. So this is x plus y plus z is equal to x plus y plus z. And so what the associative property is telling you is that if you have a sequence of operations that are all the same, so you got a whole bunch of ors in a row, it doesn't matter which one you do first. You can either do the left-hand one first or the right-hand one first. Doesn't matter. And so by putting them in parentheses, it's reinforcing the idea that I could either do the y or z first, or I could do the x or y first. And then on the multiply side, on the and side, I've got x times y times z is equal to x times y times z. And that also makes sense from your regular algebra class, that if you have a bunch of multiplies to do, it doesn't matter whether you do the one on the right or the one on the left first. You do either one. What is commutative telling us? Kind of in English. What does commutative tell us? Well, it tells us that if we have an operation like and or, we can actually switch the order of the operands. Like if I have 2 plus 3, regular math, 2 plus 3, I can either evaluate that as 2 plus 3, or I can evaluate it as 3 plus 2. I still get the same result. So the commutative property for Boolean algebra still holds true. I can switch the values of x and y, and it doesn't change the outcome. Okay, distributive. Now this one you've seen before. You've got this x sitting on the outside of something being added together inside the parentheses. You can then distribute that x through the expression. Did I do that right? I did not write that down right correctly. Let me switch that around. That should be xy plus xz. There you go. So you can actually send this x through the expression, and the x gets kind of snuggled up to the y, and the x gets snuggled up to the z, and they both get added together. So you've seen that before. It's called distributive if you run it this way, and it's called factoring if you run it that way, but it's basically the same thing. This other one over here looks a little strange. So it's just kind of the opposite of the first one. Now you have a plus over on the left-hand side and a multiply on the right, and then you can distribute that plus through the expression, and so the x gets added to y, and it also gets added to z, and the two get multiplied together. Now that one looks a little strange. You've probably never seen that one before, and certainly it doesn't work when you're dealing with just standard numbers. But it does work if you're just using ones and zeros. So I call this one the weird distributive property because you've never really seen it before, but it happens to work in Boolean algebra. Okay, identity. We've got x times 0 is equal to, no, that's not x times 0, that's x. Let's see what I mean by the v's and the hats start making my eyes go bonkers after a while. I can't tell the difference between them. So x plus 0 equals x. That makes sense, right? If you add 0 to something, you just get the same thing back. Likewise, if you multiply something by 1, you get the same thing. So that makes sense. The 0 or 1 property, x plus 1 is equal to 1, and x times 0 equals 0. And so what this one over here is saying is that if I have some Boolean variable x, which could be either true or false, and I OR that with something that's always true, then the result is always true. You know, like one weird example could be, did you eat your lunch, or do we live on Earth? Well, we all live on Earth. That's always true. At least I hope so. And then whether you ate your lunch or not, that could be true or false. But that whole expression is true because one of those things is always true. And then for the multiply side, we've got some Boolean variable, which could be either true or false, multiplied by something that's always false. And then the answer to that is always going to be false. Okay, next one is called the idempotence, and it's underlined because Microsoft Word decided that was not spelled correctly, but that's how it's spelled. And this is x plus x is equal to x, and x times x is equal to x. So some variable added to itself, or ANDed with itself, or ORed with itself, just gives you the same variable. Negation, x plus not x is equal to 1. So did you eat your lunch or did you not eat your lunch? Well, that's always true. And then x multiplied by not x is equal to 0. Did you eat your lunch and did you not eat your lunch? Well, that's always false. You can't do something and not do something at the same time. And then finally, De Morgan's, and I explained that before. If you are negating an expression, then the negation kind of distributes through, but the operation changes. So this is x plus y all negated is equal to negative x, or not x, times not y. And then De Morgan's also applies for the other set of operations. And then because we proved the absorption property, we can also write that one down. So we proved that that was true, and it happens to have a name, so I'm going to go ahead and write it down. Maybe we could use that. Okay, so these are what I will call the properties of Boolean algebra. You can find these on the internet. This table, I think you can, it's in your textbook. Once in a while, somebody tells me that one or a couple of these properties has a different name than what they found on the internet. That may be true, particularly for things like idempotence in the 0 or 1. Sometimes this is called positive or negative, or and or something like that. It has a slightly different name, but it's the same property. Okay, so hopefully you had a chance to write these down.
I noticed earlier that you used like a triple equal sign. Is that different from the one that we were using right now?
A triple equal means like these are equivalent. And the double equals just means they're equal. I'm not a big stickler, right? This is not like a math class where the symbols are the subtleties between the symbols are super, super important. So yeah, maybe I should have used the triple equals here to show that they're equivalent to each other.
Yeah, I just wanted to clarify. It doesn't really matter too much.
Okay, so for this one here, we're going to show that the left-hand expression is equal to or equivalent to the right-hand expression by simplifying this. If we can get this one on the left to look like the one on the right, then we have shown that they are equal. Now, we could do a truth tables, of course. Actually, we already did this one with a truth table. We already did this one. So now we're going to do it using this new technique. So I guess the first thing I would do is rewrite this in the algebraic form, just so that that pattern matching side of my brain that's been working with algebra for all these years kind of gets engaged, and it's easier for me to see what's going on. So I'm going to rewrite this as x times not y plus not x times not y. Yep, I got that right. It's equal to not y. And so now this becomes a problem of, do I see a pattern here, especially in regards to the properties we just wrote down? Do I see patterns there that I could apply to this to make some progress towards simplifying it? So you look at this chart and you go, does anything here kind of resemble what we have over here? What do you see? I'll flip back. You see anything here? It kind of looks like what we have here. And even if you don't see any patterns, just pretend that this is just an algebraic expression and you want to simplify it. What would you do first? I look at this.
There's a question.
Yeah.
Can you like carry stuff over the equals, or just?
I would avoid doing that.
Okay. Never mind.
So in Boolean algebra, we don't have anything like subtract or divide. We only have multiply and add. So you might be thinking like, well, what if I divide both sides by not y, right? Could I do that? I mean, algebraically, you could do that, and I think you'd probably arrive at the same answer, but I would just avoid that because we don't really have division as an operation that we can do. But I look at this thing on the left and I go, I see a common not y in both of these terms. So maybe I could use the distributive property and factor that out. Right, over here, distributive, it looks kind of like this one. I see a common x in both of these, and so I can factor out that x and isolate it. So I can do the same thing over here. I'm going to write down on the right-hand side the property that lets me do that particular step. So I use the distributive property to get from that first initial state to the next step. So now you look at this and you go, is there anything in here that looks like something I could use? Can I do something with this x plus not x?
You can use the negation property.
Yeah, let me look over here. Negation, it looks just like that. And then I got a 1 times y. It looks like we're almost there. I look at the right-hand side, and I look at the left-hand side, and go, oh, we're so close. What can I do with that 1 times not y? So I look over here, and I go, do I have anything that looks like that? And I go, yeah, here it is. Here's where I got a 1 times a something. Just gives me the something. And that was identity, I think. And now I've got the left-hand side looking like the right-hand side, and so I've shown that they're equal or equivalent to each other. Okay, let's do number 2. Now this one I'm not going to show you what it's supposed to end up being. I'm just going to say simplify this as much as you can. So now it's kind of up to you to figure out how we can get this simplified as far as possible. So take a look at this. P or Q and not P or Q. Maybe rewrite it in algebraic form, just so it's easier to see what's going on. And then look to see, is there anything there that looks like a property that we've seen? Now, if this was just a regular algebraic expression, what you might think is, well, that looks like something I need to apply FOIL to. You know FOIL, where you pair up the first, and then the outer, and then the inner, and then the last. And you know, you could do that. It's perfectly okay. But this actually does resemble one of the properties that we have. If you look over here, it looks kind of like this one over here. We've got, you know, two things in parentheses next to each other. and there's a common one in between both of them. So I look over here, I got two things in parentheses, and I have a common one in between both of them. So I end up with P, oops, not that, P times not P plus Q. And then we have P times not P. So if I look at my table, P times not P. So I got two things being multiplied together where one of them is negated. So that looks like this one right here. So this becomes 0 plus Q. Oh, and I forgot to get the name of the property, so I got to flip back. That was the negation property. And then finally, 0 plus a variable just gives me the variable, and that was identity. Now let's say you looked at that problem and you didn't recognize that weird distributive right off the bat. Because it's not something you've seen collapse down to something simpler. Instead you look at that and go, I see FOIL there. I gotta do FOIL. So why don't we go ahead and do that? So what if you didn't recognize the, what I called weird distributive? So we saw P plus Q times not P plus Q. And so we're going to do FOIL on this. So we're going to do the first, which is P times not P, plus the outer, P times Q, plus the inner, Q times not P, plus the last. And now you don't get Q squared in this case. You get Q times Q, because we don't have a square operation. All we've got is negate and an OR. Negate, multiply, and add. So we get Q times Q. And I'm just going to slide this over so I've got some space. And now we're just going to start simplifying from there. So P times not P, negation says that becomes a 0. And then the 0 drops away by identity. The QQ on the right-hand side becomes just a Q. And that is idempotence. Now, we're at this point, and now we got to start maybe looking at some different things to do. So right here, I've got these two terms, and there's a common Q between them. So it looks like I could factor that out. And this is just using the regular old distributive property we're used to seeing. And then that P plus not P turns into a 1 by negation. Then the 1 drops away by identity. And then the Q plus Q becomes just Q, also by idempotence. So long way around, but we did it. So we had to do all this just because we didn't recognize this as being this unusual distributive property to begin with. But you know what? What we did kind of there, and we could maybe work a little bit more on that, was we basically proved that the weird distributive property works, right? We didn't recognize it as the weird one, so we did the whole FOIL thing and then reduced it down, and we ended up with the same answer. We ended up with just Q at the end. So somewhere along the line, we showed that the weird distributive property actually is a true thing. It actually works. So we could show that using this technique. We could also show it by just doing truth tables for it. Actually, we did that. I think we did that when we were building those truth tables. That was actually the weird one that we did. So we had actually shown that this unusual distributive property works in two different ways. It's actually, I had a slide right over here where I was going to do exactly that. I was going to show that the one on the left is equal to the one on the right. So let's go ahead and do that. We're going to start out with FOIL. We get x times x plus x times z plus y times x plus y times z. That's a good old FOIL. And then the x times x just turns into x. And that was idempotence. And then right here, this x plus xz, I mean, that's really the weird distributive one right there, right? But we can't use that, right? Because we can't use what we're trying to prove. But what we can do is we could factor out an x out of this, right? Just using standard algebra. So nothing unusual there. And then this 1 plus, that just turns into a 1. Oh, whoops, I forgot to factor out the x right there. Okay, so this just turns into a 1, because 1 plus anything is just a 1. And then this turns into x by identity. Okay, now we can do that same little trick again. We can factor the x out of the next term. And then this turns into a 1 by 0 or 1. And this turns into x by identity. Okay, and then now I've arrived at the right-hand side. Okay, so let's do this one. Try to simplify this down as much as you can. X plus y plus not x times not y. What could you do to this first? Any ideas? I mean, so what I can't do, I can't factor the y out of this, right? Because I got a y here and I've got a not y here. So I can't factor a y out because I got two different things here. Can't factor an x out, again, because I've got an x on one side and a not x on the other. But if you just look at some pieces of this, like if I just look at this right-hand piece, that actually does kind of resemble this weird distributive, where I've got like a single variable plus two variables being multiplied together. So I've got, I've got a single variable here, and then two of them being multiplied together over there. So somebody on YouTube says, add 0 or multiply with 1. I mean, that doesn't really get you very far. But this does look like that weird distributive. So maybe we can apply it in the reverse direction. We got x plus, and now we have these two together plus these two together. So we get y times not x plus, no. When I put these together, I mean I add them together, like this. And then we're going to multiply that by y plus not y. So we're doing the distributive, but in the reverse direction. And this is going to be one of those cases where sometimes you have to make a step that makes the expression a little more complex, but it actually makes good progress towards simplifying it later. Because now we've got this situation where we've got this y plus not y, and we know we can do something with that. By the negation property, this just turns into a 1. And then by identity, that 1 goes away. And then let me get rid of the parentheses because they're no longer necessary. Now, maybe we can do something with these x's over here, but they're separated by the y. So using the commutative property, we can switch the order around a bit. We can go x plus not x plus y. And then tell me what we can do with this x plus not x.
Is it just 0?
Almost.
Should be 1.
It should be 1, yeah. If we look back at our properties here, x plus not x is this one right here. And as usual, I forgot to note which property that was, but I think that's negation.
Yeah, it is.
Okay. All right, so I end up with 1 plus y. Does that simplify further? It does. It just becomes 1. So it turns out this expression is just always true. Took a complex one and turned it simpler. And you may be asking at this point, like, what does all this matter? Like, why are we doing all this stuff? Well, imagine you're a programmer, and you've been given this expression, this x plus y plus not x, not y, as the condition for an if. And maybe it's a really important one. Like maybe it's the conditions under which this level is complete. So if you do condition X, let's say that's like, pick up all the power-ups. And then condition Y is like, kill the boss, right? So you picked up all the power-ups, or you can kill the boss, or you can do neither of those. And then that's a condition under which you'll advance to the next level. Well, it turns out that's always true. So as a programmer, you might come back to your level designer and say like, hey, I just found out that you don't have to do anything at all on level 3, and you'll go immediately to level 4. So this is always true, and so you might want to reevaluate how that level is designed. So this could be a way to take a complex condition and simplify it. Makes your program easier to understand. Maybe even makes it work a little bit faster if the condition is evaluated a whole bunch of times. Now, before I switch slides here, I want to show you a couple of other ways to solve this problem. And these were suggested by students in previous semesters who solved this in what I would say is, one of them is kind of like in an unusual manner, but it seems to work. So one other possibility was, let me start with the first expression, x plus y plus not x, not y. So one student said, this right here, I could apply De Morgan's to that. I could transform this into x plus y plus x plus y all not over it. So I took each of the variables and I inverted them. So the not x's became x and the not y became y. And then I changed the operation from and to or, and then I put a not over the whole thing. And then the next step would be to do a little substitution. Let me just say that a is equal to x plus y. And so I end up with a plus not a, right? Here's the x plus y. I just became a. Here's the x plus y here, but it's all knotted, and so it becomes not a. So this is obviously negation, a 1 by the negation property. Well, that sure made quick work of it. So I like that solution. And then I had one very enterprising student who submitted this as the answer. Probably heard that old saying, like, 2 wrongs don't make a right. But in Boolean algebra, 2 negations do make a positive, do make something true, right? So we're going to negate this twice. Right? So if I negate the whole expression, then obviously, it becomes false. But if I negate it again, then it just basically returns to the original one. And so now what we're going to do is we're going to take this first negation right here, and we're going to apply it to this whole thing. So we're basically doing De Morgan's on this. And by doing De Morgan's, we switch the signs, and we negate the variables. So this becomes not x times y times x plus y. And we just got rid of one of those nots. Now we're going to do distributive. By applying the not x, not y to both of the terms inside the parentheses. We still have this negation on top, right? We haven't done anything with that. All we did was apply distributive. Okay? And then we can see in each one of these terms we have a not x and an x multiplied together. And I think that's the, let me look what property that is. If we have x times not x, that is negation, right here. So we end up with 0 times not y plus 0 times not x. And then we still have a not over the whole thing. And then 0 times anything is just 0. So 0 plus 0, still with a not over that. And then 0 plus 0 is 0. And not 0 is 1. So when I saw that solution, I went, wow, that's pretty creative, but I guess it works. And then, you know, when I was doing this problem over here on the left-hand side, and I said, you know, you look at this over here, and you can't factor out the y because I have a non-negated y here, and I have a negated y here. So they're kind, even though they're the same variables, both y, I can't just factor it out because, I mean, like, what do you do with a not? And so it got me thinking, like, what if you actually, and really, honestly, I don't know what's going to happen here. What if we actually did that? What if we actually factored the y out of that? I want to see what happens. I mean, like, let's just think about it. If I was to try to factor out that y, I get 1 over here, right? So I factor a y out of a y, and that leaves behind a 1. But what happens over here? I mean, obviously, I get a not x, right? That doesn't change. But what happens to this not y? What happens when you factor a y out of a not y? So remember, negation, negation in terms of like not is kind of like negation in the algebraic sense. That is, like, if I take like number 3 and I apply negation to it, I get -3. And if I apply negation to -3, I get +3. So what happens if I factor a y out of a not y? Well, like, taking a step back, if I factor a y out of a y, I leave behind a 1, right? What happens if I factor a y out of a not y? Does it leave behind a 0? Or does it leave behind a not 1, kind of like a -1, right? If I factor 3 out of -3, it leaves behind a -1, right? And in the Boolean algebra, -1 is just 0. So let's see what happens, right? Now, I know here that we have this 1, and so that's always going to be 1, right? But I just want to see what happens over here, right? So now we've got x plus y times 1 plus 0. And then we have x plus y times 1, right? Is this going to work? I don't know. Maybe this doesn't take me anywhere. Now we have x. Now we have x plus 1. And then, oh, we end up with just 1. Huh. Maybe it did work. I'll have to think about that some more. Like, can you factor a non-negated variable out of a negated variable and leave behind a 0? I'll have to think about that. Does that still hold true? This could be a groundbreaking moment in Boolean algebra simplification, that if I can factor a y out of a negative y and leave behind a 0, that might change everything. So that's the general technique for applying the Boolean algebra properties to an expression and simplifying it down. For the most part, it's just a matter of doing pattern matching. Find a property that seems to match one or more of the patterns inside of your expression, apply it, and hopefully that'll make progress towards simplifying your expression. So we're almost at the end of the lecture portion of today. We're going to take, after I show you this next little thing, we're going to take a break, and we're going to come back and I'm going to show you the lab or the assignment for this week. It's going to be a lot of fun. So let me give this a little preview. Let's say you've got this expression, a plus not a times b, and you want to simplify that. Now this happens to be the absorption property, so we know that this simplifies down to just a plus b. But what if you didn't know that? So you can go through the whole distributive, negation, identity stuff, or you could do this visually. There's a technique for simplifying expressions visually by drawing a picture. And here's what the picture is going to look like. I'm going to draw a grid. And down one side, I'm going to put one of the variables in both of their positive and negative forms. And then I'm going to look at my expression. I see the a here, so I'm going to put 2 dots on the a row. This is the a row right here. And then I see the not a b, so I'm going to put a dot at the intersection of not a and b, which is right here. So I end up with 3 dots in this grid. And then I'm going to look at those dots, and I'm going to start circling some of them. So I'm going to circle this pair, and I'm going to circle this pair. I'm going to kind of join them together. And as a result of joining them together, I obviously have as the simplified answer a plus b. So this circle here represents the a circle, and this is the b circle. There, I just simplified that expression. I didn't have to do a whole bunch of steps. I just drew a picture. This is called now I'm not quite sure of the pronunciation. I pronounced it Karnaugh, and I've been pronouncing it that way for many, many years, although it could be Karnaugh. So for this second problem down here, same idea. You draw a grid. Down one side, you put one of the variables, and across the top, you put the other variable, and then you start putting dots in there. So there's going to be a dot in the top left, a dot in the top right, and a dot in the lower right. And then we end up with a circle here and a circle here. So the answer is obviously x plus, not y. And I think we did that one as well. So that's what I'm going to show you on Monday and on Wednesday. On Monday, we'll do Karnaugh maps with 2 and 3 variables. And then by Wednesday, I'll show you Karnaugh maps with 4 variables, and also how you can use them to solve more complex digital logic problems. Make practical problems, like I want to design a circuit, an actual real live physical circuit that maybe displays a bar graph depending upon the volume of a sound. Or I want to do one that turns digital 1s and 0s like into an LED display. Like if I have the number 1001, which in binary is 9, how would I actually turn that into the number 9 that you could see on an LED display? And so what you basically have to do is come up with the Boolean expressions for each one of those segments in the display, plug them into some Karnaugh maps or simplify them using algebraic properties, and then come up with a circuit that actually implements that particular driver for that segment. And then I've actually worked that out. I've done it in a logic simulator, and we can plug in a binary number and see it display the actual binary digits. The actual, sorry, not binary digits, see it display the decimal numbers. So yeah, so this is an introduction to Karnaugh maps. And so we will do that next week. But for now, we're going to take a short 5-10 minute break. And then we'll come back and I will show you the assignment for this week. And actually, the people who are on YouTube, you can do this too, because it's not one where I have to give you an assignment page. It's something you can just go to a website and you can do it yourself. Okay? So I'm going to pause the Zoom video so that they don't see the 10-minute break, but the YouTube one I can't pause, so I'll just put on some music.
Recording stopped.
What I need is like we'll be right back message, but I haven't gotten around to making one of those. I've got a couple of people watching on YouTube. How are you guys doing? I'm kind of quiet. Well, thanks for telling me it's an awesome explanation. I don't know exactly when you posted that, but something in the stream today kind of struck a chord with you, and you liked what I said. How many of you watching this stream on YouTube right now, and I think there's only maybe 1 or 2 of you, also watch the one I do on Tuesdays and Thursdays?
Recording in progress.
Hopefully you got a chance to go take a little break, and why don't we quickly go over the assignment for this week, and then we can continue this conversation that started on Zoom, which is what's a good programming language? What's my favorite programming language, and what are good programming languages for beginners to learn? So the assignment for this week is actually kind of fun. It's not a programming assignment, this is a game. So here's our assignment page, and basically you're going to be constructing the basic building blocks for a computer. So this is called the NAND game, and you're going to start with just a NAND gate, and from that build up all the other fundamental operations, and then from there build up pieces of a computer like an adder, port multiplexers, comparators, switches, and so forth, all these pieces. You're not going to go through the whole process. For this particular assignment, you only have to go through, I think, the first 10 or so levels. There is another assignment called a deeper dive where you can go and take it all the way to the end. But for this assignment, it's just required to do the first 10 levels. And so at the end of the assignment, you should take a screenshot of the progress screen that shows that you've completed the levels in the first 3 columns. And so what you're going to do is you're going to turn in a Word document or a PDF that has screenshots of this one that I just showed you, plus the levels showing all green, which means you passed the levels for the XOR level, the full adder, the multi-bit adder, the less than 0 level, and the switch level. So just a few of these in here just to show me that you did it. So let's go take a look at the NAND game itself. I've got it opened up in this tab here, and I'll kind of walk you through the first couple of levels. So it says, welcome to the NAND game. You're going to build a computer starting from basic components. The game consists of a series of levels. In each level, you're tasked with building the component that behaves according to a specification. This component can then be used as a building block in the next level. The game does not require any previous knowledge about computer science or computer architecture. It does not require any math skills beyond some basic addition and subtraction, although it does require some patience. Your first task is to build the NAND component. This is actually a new one. Since I took that screenshot of the NAND game, this level didn't exist. So this is a new level number 1, where you actually have to build a NAND out of what's essentially buttons or transistors. In this case, they're called relays. On the diagram on the left is the exact specification of the task. Click Help level if you want further information. So our job is to build this truth table out of these components. And so step 1, drag components from the toolbox into the blue area. So let's go ahead and do that. I'm not sure which ones we're going to need first, but we'll probably need both of them. Step 2, tap or drag the triangle to create a connection. So what we're trying to do is using these relays. And so what basically happens is if you energize the coil in this relay, this bar will be attracted toward the coil. This is the way an actual relay works, an actual electronic relay works. This bar will be attracted to the coil and will make this connection, allowing electricity to flow from here to our output. And then this relay over here works in the opposite way. When you energize the coil, the bar is attracted to the coil and it disconnects the connection. And so our goal is to make this truth table, which is the NAND truth table, out of these components. So let's see if we can do this. So I've got 2 inputs, A and B down here. I've also got power, which is always a 1, and that could be also be used to pass some power through to the output. So if we want help, there's this level help up here. But let's see if we can get somewhere without doing any help. So if I have A and B both being 0, I want to output a 1. If A and B is if either of them is a 1, I also want to output a 1. And if both of them are 1s, I want to output a 0. Okay, so let's see. So if either of them is a 1, I want to output a 1. And if both of them are 1, I want to output a 0. Well, what this one here will do, what this relay will do, is it'll output a 1 if the relay is energized. And this will output a 0 if the relay is energized. So what happens if I do something like this? Like if I just connect this here and this here, and I connect this to here, then what will happen is if A is a 1, it'll energize the relay, and then power will flow through. Oh, and then the value of B will flow through. And right now it's saying that's wrong. That's all wrong. But what if I do this? What if I take the output of that and then make this, I'll connect this over to here, and I'll connect this to here. And that works. Okay, so if A and B are, if A is energized, then the value of B will flow through. So if A is energized, which is this one right here, then the value of B will flow through, and I'll get a 0 as the output or a 1 as the output. And if A is not energized, just the value of 0 comes out. And then what this other relay does is it flips that. So if the output is a 1, then the power going through will become a 0. And if the output is a 0, then the power going through will become a 1. And so it basically just negates, this relay up here negates the output of this one here. And so it turns out this one works. So what we've just done is we've built the NAND gate out of just 2 relays, or just 2 transistors, if we were doing it actually in semiconductors. So let's check our solution. We got all greens, so we're going to move on to the next level. So now we have a NAND gate. We've built NAND, so now we can just use that. Our next task is to build an inverter component using the NAND component. Now, we already saw how to do this. We did this last time on paper. Remember how to do that? You take both inputs and you feed them into the input becomes both the inputs for the NAND, and then this connects up to here, and that should do it. We got all check marks there, and that worked. So here's what it looks like. We've got NAND, same input going to both, or our input going to both inputs of the NAND, and then the output going to the output of the circuit. So the next step is to build AND out of NAND and NOT. And we did this one also. So if you look back at the session from last time, you can see how to build an AND from a NAND and a NOT. The level after that is to build OR using NAND, NOT, and AND. The level after that is to build exclusive OR out of those same gates. Now we have OR as well. And then we have half adder, full adder, and again, if you watch yesterday's video, you'll see how to do those. Multi-bit adder, and we go to levels over here. We can see we're working our way through these. So you have to get all the way up through plumbing. So logic gates, arithmetics, and plumbing. And then if you want to do that deeper dive, finish this all the way through. Actually, go as far as you can, but you actually end up building a full working computer. Actually, I think it's a computer that solves a maze. Basically, it's a computer for a robot. It's like a robot control that solves a maze. And then from there, you start building a programming language. And the person who designed this website has really made a lot of progress on this. They're starting to do floating point stuff. Wow, this is all new. All this stuff down here. XNOR, left shift, right shift, multiplication, floating point. Wow, that's great stuff. And this is all new as well, so starting to build a programming language. So that's your assignment, is get through the first 3 columns of the NAND game, and then for the deeper dive, get through the rest of the columns, at least on the top half, or at least I would say get over here to the programming one. Okay, so there's not much, else to show except just work your way through. Again, on all of the levels, well, not all of the levels, but on many of the levels, there's a help button that you can click on to get some hints about how to solve that particular problem. And also you can go look in the previous video we did from Monday, and also I think you can look in your textbook. There's a chapter that we didn't do. I think it's chapter 4 that goes through some of this as well. So you can look in there for some hints. And if you're really interested in this really looks cool, then there's a website called nandtotetris.org, I think. Yes. And this is a textbook that is freely available, and a lot of universities use this as instructions for building a working computer out of nothing more than NAND gate. The computer is all entirely simulated in some tools that you download and install on your computer. So it doesn't run like, anything fast like, an i7 or an i9 or anything like that. But it's a working computer, complete with a programming language, a basic operating system, a video display, a keyboard or a controller input, and you actually build a little Tetris game out of it. So same idea, start with just NAND gates and then build up the whole computer from there. So again, if this looks really interesting to you, this NAND game, then it's actually based upon the concepts that are in NAND to Tetris. But it's a kind of a version of NAND to Tetris that can be built entirely in your web browser. And I believe there is also a Coursera course. One of those free online, there it is, free online courses that you can take. Build a modern computer from first principles from NAND to Tetris. And this is a course that you can take that is kind of self-paced, and it works your way through that textbook, and there's programming assignments to do, and it will automatically check to see your solutions are correct. And then if you pay a few dollars, like $70 or so at the very end, you can get a certificate that says that you completed this course. Okay, so that's basically all I had for today. Any questions about the assignment? Okay, so somebody asked me, Dorian asked me, what's my favorite programming language? And I started posting some stuff in chat. And at first I thought this was somebody who asked me that same question yesterday, but I guess I'll have to answer that question for the people who asked it to me yesterday. And I was at the end of my stream yesterday, so I said I don't have time to answer this question. But the question is, what's my favorite programming language? And I don't really have like a favorite one. It depends on the situation. If I'm writing a application that needs a graphical user interface, like a desktop application, I'll probably just use Java. Why? Because I know it can do GUI apps. I'm reasonably familiar with how they're done. I haven't done really big projects, but I know I could probably cobble one together. But it's very rare for me to actually write desktop GUI apps. So I don't do it often enough to kind of keep my skills up in that area. Most of the programming that I personally do are basically single-use, one-shot programs that do one little thing and then I'm done with it. So I don't want to write a fully fleshed out program with buttons and menus and stuff like that, especially when I'm just doing one little thing. A lot of the programming I do is on the command line. I might have some data files that I need to analyze. I might have some databases I need to access and pull data out of. And so for that kind of thing, I learned Perl a long time ago, over 20 years ago. And back then, Perl was like the language to do that sort of thing. It was great at text manipulation. It was great at the kinds of things that system administrators on Linux machines need to do to automate tasks, to look through log files and pull out data that helps them analyze the performance of their machines. So that was the language that I learned, and that was it's still very comfortable for me to use. A lot of people say Perl just looks like gobbledygook, right? They can't really read it because there's lots of symbols and there's lots of shortcuts in there. So again, it's great for people who really need to like write a program quickly, get the job done, and then move on to the next thing to do. And so if I have to write a program that needs to maybe access a website and pull data off of it, or write a program to be a very quick internet application server where I have to serve up some data to a client, you know, Perl is great for that because the Perl is described as being kind of like a Swiss Army knife of programming languages, right? The Swiss Army knife's got all these little tools in it. It's got knife and scissors and a saw, and you know, none of those tools are like excellent at doing any one task, but you got a lot of tools at your disposal. So I tend to use Perl. Obviously, if I have to do web programming, then HTML, CSS, JavaScript, PHP is like the way to go these days. I don't particularly like any of them. I mean, I hate programming in PHP, but I have to do it because that's what's used these days. What was I going to say? JavaScript is barely tolerable, but if you have some libraries like jQuery, then it's a lot easier to program in JavaScript, although there's a huge learning curve with any of those libraries. But once you kind of understand what's going on, it just makes a lot of the tedium really, really easy. Like jQuery is great for pulling data off of a web page to say, like, you know, whatever the value of this fill-in form over here, copy it over here. It's great for pulling data, doing background web requests to a server, and pulling data off that server and dynamically putting it back on the page. So there's lots of frameworks for doing that kind of stuff. If you have to do that all by hand, it's just a pain. Python, you know, I know Python enough to get by. I don't use it a whole lot. I mean, obviously I know it enough to be able to teach a class like this and use Python, but the really nuts and bolts of it, I haven't gotten to it that much. I mean, like I said, I know enough. I know a lot of languages enough to get by. Everything else I just look up online. I know a lot of languages, but again, just kind of superficially. And the reason there is it's great to be able to just look at a program and kind of get an idea about what's going on. Back when I was in college, I used C a lot, so I'm pretty comfortable there. I didn't really ever get around to learning C++, so I don't know that one really well. C, of course, it's great if you want to write high performance programs, but you know, most of my programs, I'm not interested in performance. I'm interested in just getting the job done. And so that's why things like scripting languages like Perl and Python can work well enough. Do I think Java is a good language for beginners to learn? I'm not entirely convinced that that's true. Java back in the 90s was a fairly small language. It was easy to get your head around the whole thing. Now it's just grown. Every year they come up with new features for the Java language. And all those features are available for beginners to use. And that could be part of the problem. That a beginner might type in a fairly small program, make some little innocent mistake, and get an error message that is just incomprehensible because it uses terminology that the beginner doesn't know yet. And so a lot of universities are switching over to languages like Python. Python is easier to get into. There's not as much syntax to learn. You know, there's no semicolons, there's no braces, but you do have indentation, but you were going to indent anyway, right? And so Python can be good as a beginning programming language, but I'm not convinced that that one is well suited for the task either. It has its rough edges, like any programming language, but the rough edges can creep in a little bit earlier than other languages. So for beginners, what you really need is a programming language explicitly designed for beginners. I mean, like that's the main design goal, is a language specifically for beginners, not a language that happens to be friendly to beginners like Python, but is really for seasoned, experienced programmers, but a language targeted exactly at beginners. And languages like that need to have good error messages. like error messages that are understandable to a beginner. And it needs to be simple enough that you can write the kinds of programs that beginners need to write. And I think actually a language like that should have a ceiling, that the beginner starts out and they start writing more and more sophisticated programs, and they bump up against a wall, or a ceiling in this case, where they can't write something more advanced than that because the language that they're using simply lacks either the libraries to do it or the ease, the ability to do those sorts of things. Like maybe you can do a programming language that does very simple GUI stuff, but anything more complicated than maybe a couple of buttons and a fill out form is just not possible in that language. And so what that does is it lets the programmer know that, hey, you're done with this tool. Now it's time to move on to another one. You know, it's kind of like if you were, learning carpentry, right? You start with hand saws and a hammer and nails and screws and manual screwdrivers. And those are all great because it teaches you the fundamentals about how to cut things and how to put them together and have them hold and be secure. But eventually you're going to bump up against the ceiling. We're going to say, like, well, if I want to build this table, I could do it with the hand tools, but it's just going to be I'm just going to be wasting my time. There are other tools that will help me do that more easily. I could use a power saw, and I could use a power planer, and I could use power tools, but I shouldn't be using those power tools unless I already know how the manual tools work. The nice thing about the manual tools is they give you immediate feedback about whether they're working or not, right? Wow, this screw is really hard to turn in there. Well, that's because you didn't drill a pilot hole. If you did that first, then putting in that screw would be easier. Oh, I understand now. Whereas with a power screwdriver, just put that screw right in, and it doesn't care whether you drilled a pilot hole or not. And then you end up splitting the wood, and then you don't know why. So it's like you get error messages that are incomprehensible. Does that make sense? So are there programming languages out there that are designed for beginners? There certainly are. We don't use them. And the question is why? And I think that there's a lot of pressure from both, like at the high school level from parents and at the college level from students who want to use like what the professionals use. Right? We should learn Java because that's what the professionals use. Or we should use C because that's what the professionals use. And to me, my personal opinion on that is, well, let's say you're learning to be a doctor. So we should go in and we should start doing surgery on the first day because that's what the professionals do, right? Right? No. What do doctors in training do? Well, they work on scaled down, like they learn the basics first. You don't practice on a real live human first. You practice on a dummy. You don't even do that first, right? You learn how to do basic stuff first. You learn about all the parts. You learn the terminology. You don't actually operate on real humans until you're like actually almost out of medical school, right? You might even not do that. You might not do that until you're like your internship and your residency. You do that way later. You don't use the professional tools until later in your education. You use beginner's tools first. And then you hit a ceiling. You're like, I can't do that because I don't have access to an MRI. Or I don't have access to an X-ray machine. And so you realize what the limitations are, and you can move beyond that because now you're able to evaluate the tools you have and say, these tools are not good enough for me. I need to move on to another set of tools. Whereas with a programming language like Java, it's got a huge, tall ceiling, right? And so a lot of people can kind of get stuck in this rut where they say like, well, I could do this program if I just knew a little bit more about Java. And I log on to discussion boards that are frequented by beginners. There's some on Reddit, there's some on Discord, and they're kind of like always asking the same questions, like, how do I know when I become a proficient programmer? How do I know when I become an expert? And they say, well, there's not really like a dividing line. It's not like you cross this line and suddenly you're an expert. But languages like Java always like have more to learn. There's always more up there to learn. And you always feel like I'm never going to reach the top because there's more to learn. There's more libraries out there. There's more frameworks. There's more this, there's more that. Whereas I think if you have languages that are kind of like tiered, where you realize that you've crossed over some threshold, I can't do what I want to do with the tools I have, so I got to cross over to maybe another language that has those tools. Or maybe I can start introducing new libraries into this language and let me do that thing. You go, oh, okay, so now this library lets me do this thing that was really tedious to do before using the hand tools, but now I can kind of automate that. So I understand what's going on. So that's why when I teach the Intro to Programming class, and even the second class, 12 and 13, I tend to start with really basic stuff, and I see how far we can go with just the basics. And then we hit a ceiling, and I say, okay, now we've hit that ceiling, now I can show something else to you. And I have to use Java because that's what we use at our institution. I'd probably rather not use Java, but that's what we have to use. And so I try to structure it so that I show you as little of the language as possible and see how far you can go with just those basics. Oh, you're mentioning Code 12. I actually love that tool. So that was the same idea. It was a subset of Java, a very small subset of Java, and you had these tiers, right? You know, you had like tier number 1, in which you could only do really, really basic things, and then once you ran up against a wall, you opened up tier number 2, and then you could do a little bit more, and then you could do a bit more. And one of the ideas behind Code 12 was to make, first of all, to limit the scope of the language, so you didn't run into things like enums and interfaces and public and private until you were ready for those things. And the other was to give you good error messages. If you kind of limit the scope of the language at first, then you can give really good error messages, because you don't have to worry about giving error messages for language features that the programmer has never seen before. You can give error messages about only the things that they are supposed to know. And so that Code 12 is actually informed by a lot of the stuff. I worked with the guy who developed that. He was one of our faculty here. And so I gave a lot of input on what I think would be a good way to structure this. He went off and did it on his own. He actually programmed it on his own, but I showed him the resources about how to structure the tiers and this idea of having levels that you could go through. Code 12 is actually based on that idea. There are other languages out there like older ones like BASIC and Pascal are actually pretty good for beginners because they're fairly limited in what they can do, but they can do a lot. There's another one out there called Pyret, P-Y-R-E-T, also designed specifically for beginners. What else is out there? I mean, there's like the kiddie languages like Scratch and Alice, which you may have used in some high school or elementary school. Those are great for beginners too, because they get the concepts down, and of course you hit a ceiling pretty quickly, and you realize it's kind of a pain to drag and drop expressions into there. If I want to do a complex math expression, doing it in Scratch is just a real pain, right? Because you got to drag and drop every little thing in there, and you go like, if only I could just type them. Well, you know what? Maybe in your next language you should be able to type. So I like this idea of hitting a ceiling or a wall and realizing that if only I had this next feature, then that would make my job easier. And I think that's what kind of gets the brain learning about these things, is to struggle with a limitation and then be able to get through that limitation by moving on to the next tool. When I was in college, what we did was our first term was Pascal. That was the introductory language. And the understanding was we would take Pascal for just one term, and then we would throw it away and move to something else. So we did Pascal once. The second course was assembly language. So we learned assembly language right after Pascal. And what that did was it taught us, we learned a high-level language first, and now we learn a really low-level language. And the low-level language teaches us like how the machine is actually working behind the scenes and what's going on with, what does it mean when you get a bus error or segmentation fault, right? Because your program actually committed that error. You're responsible for solving that. Told us about resource limitations and how to break down a problem into really small pieces. And then, so that was the second term. And then the third term is when he started learning languages like C. C++ didn't exist back then, so we had C. And that was pretty much the go-to language for all the rest of the courses. So Pascal first term, assembly language, and then C from there on out. And that was great because by the time you graduated, you knew at least 3 languages. And it can be tough for some students these days because they get all the way through college and they've only learned one, Java. And so they might wonder, well, why should I bother learning anything else? Java does everything I want it to do. There's some wonderful languages out there. There's thousands of programming languages out there. It's kind of like, why should I look at any other websites? Google has everything. Well, there's some great websites out there that are, don't do what Google does, right? Let's see, catching up on the chats here. At my university, we start with 2 semesters of C language, and then we go to Java, and then web languages, and then Python for data and arithmetic analysis, and also for like data science and things like that. And then, yes, you also learn assembly and computer architecture. So that's great that by the time you get out of your university, you know C, Java, Python, and assembly language. So by that, but 4 languages. That's pretty good. What's in my future? I would like to learn Rust, not the video game Rust, the programming language Rust. And I would like to do more with quantum computing myself. There's not much to do there, but I'd like to learn more about it. We may get a chance to do quantum computing here in this course, way at the end of the semester when we've got a little bit of free time. Whew, I feel like I just talked for 20 minutes. So, how about you? Do I play video games? Not really. As an adult, you find you don't have a whole lot of time for these things, especially when you have kids. I play Minecraft and Roblox with my 8-year-old. And my 16-year-old plays, pretty much everything. Rust, primarily. This week it's Rust, and next week it'll be something else, and then like 2 months from now it'll be back to Rust again. So he cycles through a bunch of games. So he'll play like one of them like full bore for a week, and then get bored of it, and then move on to the next one. Minecraft and Roblox, that counts as video games. Does Wordle count also? I play Wordle. It's like, okay, I have 5 minutes to play a game. What can I play in 5 minutes? What are my thoughts on C versus Rust for kernel development? I don't know enough about Rust to be able to tell you that answer. Rust is kind of positioning itself as a replacement for C, for system programming, for doing low-level, accessing the hardware directly as best you can. So that's kind of like why I want to learn Rust, is to see how it, what's the right word there? To see how well it positions itself as a replacement for C. But I've only dabbled. I've looked at the tutorials. I've run a few tutorials, and then like video games. Like I don't have time for this. I have to prepare for tomorrow's class, and I have to do this and that. So it's kind of like one of those summertime projects. During the summer, I go, I'm going to learn a little bit about Rust, and then it doesn't happen. But it's definitely on my list of things to do. Do I know that I can make logic circuits in Minecraft, but it takes a long time? Yeah, I've seen some of those, like working computers. I think somebody built like an actual Apple computer, one of these old style Apple computers in Minecraft. Yeah, it takes a long time to do something, but it's kind of cool that Minecraft is what's called Turing complete, which means you can write programs in Minecraft. And it's all because of the redstones, right? The redstones implement the logic gates, ands and ors and nots, and once you have those, you can build a computer out of it. So those are pretty cool to look at. I've seen things like calculators where you go and you basically toggle in binary numbers using the toggle switches, and then you press go, and then the answer appears on a brick wall as digits that you can see. And if you take a look behind, you can see all the blocks moving in and out as act as registers and adders, and it's kind of cool to see that. Do humans make decisions in a binary way when it really gets down to it? That's a good question. I don't know the answer to that. I don't think anyone knows the answer to that yet. They're working on it. So we're asking basically, are humans computers? Well, if you just look at like an individual neuron, one single neuron, what you see is something that has basically no resemblance to intelligence at all. It's just basically a little cell that reacts to stimulus inputs. It's got some inputs, it's got an output, and based upon the combination of inputs coming in, you get an output. That's all it is. It's kind of like a logic gate. So the real fundamental question is, if we put trillions of logic gates together, will you get intelligence, or do you still just get a robot? Is there something different about humans, or animals in general, that makes it fundamentally different from just a computer? I don't think we know the answer to that yet. So one thing about robots and computers is if you give them the same input, you'll always get the same output. There's essentially nothing random about a computer. At least nothing designed into them is supposed to be random. So is the same thing true for a human? If you could know everything about its input, if you could know everything about the state of the human and its sensory inputs and what's happened before in the past, could you predict the next thing that was going to happen? Or is there something random about humans? I don't know the answer to that. But I kind of suspect that with the pace of technology, we might find out the answer to that, or at least get some insight into the answer to that. Probably within, I'm guessing within the next 40 years. And it may not be, do we know whether humans are just complex computers? We might approach it from the other end. Is it possible to make a computer complex enough that it's actually intelligent? I think we're getting there. We certainly have computers that appear to be intelligent if you restrict the scope in which they're operating. Like to have computers that could recognize images or diagnose medical diseases. Oh gosh. We have computers that can do that now, which we didn't have 20, 30 years ago. That seems amazing. You got computers now that can diagnose certain diseases better than doctors can. Certain diseases, not all of them, certain diseases. You got computers now that can predict what's going to happen to a person, let's say 3-6 months from now, based upon what they're buying in the store now. So the computer can somehow sense subtle changes in buying habits to know what's going to happen to that person in 3 or 6 months. That's pretty cool. And maybe you're wondering what I'm talking about. What I'm talking about is there was a famous instance about 6-7 years ago where Target, the department store, you get these little flyers in the mail, or used to at least, little booklets in the mail with coupons in them. And the coupons were based upon your buying habits. If it noticed that you always buying sporting equipment, it'll give you a coupon for a baseball glove or a bat or something like that. Particularly if it notices that you buy these things on a regular schedule. If it notices that you buy a new baseball bat and a mitt at the beginning of every baseball season, then next year, at the beginning of baseball season, they'll give you a coupon for those things, right? So they notice these little buying habits and they send you coupons based on that. Well, in this particular case, a family got one of these booklets and it says, "Congratulations on your new baby." Well, no one was pregnant in the family. Why is anyone, expecting a child? Well, it turns out the daughter was unknowingly pregnant. She didn't know she was pregnant, but it turned out she was. Target was able to figure out that she was pregnant before she actually knew that she was pregnant. How? They looked at her buying habits. Now, it doesn't say in the articles explicitly what Target was looking at, but my guess is that a newly pregnant mother or mother-to-be starts buying different things, particularly things like nausea medication, right, for morning sickness, right? If suddenly you're buying that and you've never bought that before, and suddenly you're buying things for, I don't know what else expectant mothers start buying when they're early on in a pregnancy, but it's enough that Target was able to figure out this person is pregnant now and is going to be expecting a baby in 3 to 6 months. Needless to say, the father was quite upset. And as a result of the publicity on this case, Target had to change the way that they do those little booklets of coupons. So now, instead of making a bold announcement like, congratulations on your new baby, what they'll do is they'll just slip in a coupon for, let's say, diapers, like in amongst the sporting equipment and the food and the stuff you would have normally gotten. You just slip one of those coupons in, and then just see if you use it. You might just Google for that. Google for like a Target, pregnant daughter or something like that, and you'll find the articles that described what happened back then. So imagine you could take that a step further. Can we predict? Now, I'm really stretching things here, but this is not too far-fetched. Can we predict that a crime might happen based upon some visible things that a person is doing now? So, like, is a person planning on committing a crime based upon some behaviors right now? I mean, that's not that much different from the Target situation, is it? But the real danger there is, would law enforcement do something about that? Could they say, like, well, our computers say that you're going to be robbing a bank tomorrow, so we're going to arrest you now? And you probably know there was a whole movie about that, right? But back then, when that movie came out, it went, that's just ridiculous. Oh, now we are like in that world where a good data analysis program could figure out if you're planning something tomorrow based upon what you're doing today. Okay, well that's like the dark side of artificial intelligence. What's the bright side of it? Well, the bright side of it would be maybe jobs that we sort of take for granted now could be replaced by either robots or computers. I personally think if you're in education now, whether it's high school or college or elementary school, you need to be thinking about, and it's really hard to do this, right? You're predicting the future basically, but you need to be thinking about, could the job that I want as an adult be replaced by a computer? And it's really shocking, actually, to me, what jobs can be replaced by a computer. Who would have thought that computers could replace doctors to diagnose the diseases? Well, it turns out they can in a very limited way. But they can. But it won't be long now before they can do a much better job. Oh yeah, the movie was called Total Recall, about arresting people before they committed a crime. So I think that jobs like truck driving, delivery jobs, will probably be replaced by a computer pretty shortly. We already have self-driving cars, right? So what about self-driving trucks, at the very least? Some jobs are already partially automated. I remember seeing a list, again, about 5 years ago, of like jobs that could definitely be replaced by computers, jobs that might be replaced by computers or partially replaced, and jobs that definitely can't be, or at least as far as we knew, definitely can't be. And it was a huge list. Like the list of jobs that definitely can be replaced were things like truck drivers, restaurant workers, basically service industry stuff right, could all be replaced by robots and computers. And then the partially replaced were things like accountants, computer programmers were in there too, and you know, a lot of professional fields like nurses and could be nurses and you know, skilled labor basically could be replaced. And I thought, what, accountants, computer programmers, we can be replaced? And I thought, well, yeah, actually, we have like IntelliSense in our IDEs, right? We start typing a few keywords and it goes, oh, it looks like you're writing a function. Would you like me to like build the template for you? I mean, isn't that basically like the computer doing part of my job for me? Or even that little pop-up that shows you like, here are the suggested variables or function names that you could use right here. I mean, isn't that like partially replacing my job as a programmer with the computer? The compiler itself, isn't the compiler doing a lot of work for me that I would otherwise have to do by hand? Yeah, so yeah, my job has already been partially replaced by a computer. You know, accountants. I mean, even when they use their tools like Quicken and Excel and stuff like that, the computer's already doing part of their job for them, right? They're no longer calculating things by hand on grids of paper. They're using spreadsheets to do their job. And now increasingly they're using computers to make predictions. Like, should I invest in this stock or not? So the computer can look at past history and look at future news reports, not future news reports, but you know, future predictions about what's going to happen and say, yes, buy this or don't buy this. So already we're seeing computers make suggestions to brokers and accountants to do the part of their job. So, you know, you should be thinking about positioning yourself so that you've got a job that can't be replaced by a computer, or maybe only partially, where the computer is assisting you rather than working against you. Do I think the job of building computers that build computers could ever be replaced? That's the big question, right? If we ever have computers that can build computers, then that's what they call the, what do they call that? Is it the singularity, right? When basically computers get powerful enough to build replacements for themselves and they can self-reproduce. But already we kind of are there. If you want to build a new computer system kind of from scratch, you're going to use automated tools. You're going to say, this is the way I want the computer to behave. This is the task I want it to do. Now go out and design the circuits to make that happen. And the computer program takes over and it just does that. And then you just punch the button that sends the order off to a fabrication facility, and then they send you the computer back a couple weeks later. I mean, like, it's almost completely automated at that point, right? The part that isn't currently automated is you, the programmer, decide what that computer should do. That's the creative part of it. And the rest of it is all automated. Let's see, I watched a video the other day about game development and how worlds inside a game can be created with an AI. You don't need artists anymore to make character models. You just type in the characteristics you want and then it designs the characters for you. Yeah. Actually, it reminds me. Let me see if I can find this website. Here it is. This is called Wombo. Here's the website. app.wombo.art. You type in a phrase, a prompt, and it paints a picture for you. The prompt can be anything, right? It could be like a sentence out of a book. It could be like a few keywords. So what prompt could we type in here? This is the creative part of it, right? I'm trying to think of something that would cause this AI to draw something for us. Why don't we put like sleeping by a stream with trees, right? That's kind of a goofy prompt here, but then let's pick a style. Let's go with pastel. There we go, create. And then the AI takes over and it paints this picture for us. And then at this point, you can take a screenshot of it, or you can order a print, or apparently you can mint this as an NFT. But look, it's kind of like a artsy. Here's a stream here. There's some trees. There's a guy sleeping there, right? Let's try something else. I don't know. May the force be. Let's see what it does with you. Let's do steampunk. Right? Will it create the same picture every time using the same prompt? I haven't played with this enough to know what'll happen there. Whoa. Does that remind you of Star Wars or not? Computers building computers. Let's go with, I don't know, rose gold. Well, I don't know about that. It looks like a bunch of, well, it looks like a bunch of buildings, right? So it didn't interpret building as a verb. It interpreted building as a noun. But that's a cool picture. Let's try it. Someone asked if we do the same thing again, will we get the same picture? Doesn't look like it. This looks different. Yeah, that's different. So you get it different every time. So now you're thinking, go great. Now the artist can be replaced. But again, it took a little bit of creativity on our part to come up with that phrase to get it started. But then after that, the computer just took over. So where does that leave us? Like I said, think about positioning yourself so that you're training yourself for a job that can't be done entirely by a computer. Kind of hard to predict the future, but you might want to see if you can find one of those lists of jobs that can be replaced by a computer and jobs that can't be replaced, and see where the job that you want falls in that list. And then keep an open mind, because just in the past 10 years, computers can now do like so much more as far as artificial intelligence than they could 10 years ago, and it's stuff that I would not have thought that they could do. Now I cease to be amazed, right? They come up with a new news article comes out. Computers have now done X, Y, Z, and I'm like, oh, that doesn't surprise me now, because we've been on that track now for the last 10 years. Anyway, we've kind of reached the end of today. We talked about the lab assignment for about 10 minutes, and then we went on this whole thing about programming languages and AI and the future of computing. So, hey, I hope you have a good weekend. Do that AND game. Take it as far as you can. It's kind of fun. And then I will see you on Monday. We'll be in on the end of chapter 3, is it? Where we're doing Karnaugh maps. I don't think Karnaugh maps are in the book. So the material you'll get will be out of the sessions we do, plus you can find some resources online. All right. Well, I think I'm going to end it here. Hey, thanks for chatting with me, and I will see you next week or tomorrow. If you're in the C programming class or you want to tune into that one, then 9:30 tomorrow morning. Take care. Bye-bye.
Thank you.
And people on YouTube, same with you. Thanks for sticking around. And I'll see you next week. Have a good weekend. Bye-bye.